Hello, today we're going to talk about some biological redox reactions. We'll go over several examples. We'll show you some examples that can occur either via 1 electron or 2 electron transfers. So let's look at some of these biological oxidizing agents. Most common one is dioxygen or molecular oxygen. Dioxygen behaves a bit different than its Lewis structure would imply. Its Lewis structure implies that all the electrons are paired. If we create a MO diagram and fill it up with electrons, though, we can see that we actually have 2 unpaired electrons in the highest occupied molecular orbitals. These then would imply that dioxygen acts as a diradical, and it can accept electrons. In fact, it can react with H plus and 4 electrons to form water. It can also get reduced to some dangerous and nasty things such as superoxide and peroxide. Let's take a look at another oxidizing agent, or one that's called FAD, or flavin adenine dinucleotide. It's a quinone and can accept 2 electrons at a time or 1 electron at a time. Let's take a look at the 2 electron mechanism first, where we can take a hydride, react here, electrons flow up and all the way up to the nitrogen. We can then protonate this to form our FADH2, okay, or a hydroquinone form. We can also do this via a 1 electron mechanism, where we can add 1 electron, and again with 1 electrons we use a single-headed arrow where it's going to react there, electrons flow over here and up. We can then protonate this form to form our semiquinone. This can undergo another 1 electron exception and then protonation again to form our hydroquinone form. Another good biological oxidizing agent is NAD+, shown here on the right. NAD+ accepts 2 electrons at a time, or in the form of a hydride. Let's take a look at this reaction with an alcohol and oxidizing an alcohol. So in this case, we can deprotonate the alcohol, electrons flow down. Our hydride, in other words, our hydrogen plus the 2 electrons, gets delivered to our NAD+, and we can draw our electrons moving down to that nitrogen. In other words, it's a sink for these electrons to form, in this case, NADH. The hydride doesn't have to come just from alcohols. Let's try this oxidative decarboxylation. And in this case, we can get our electrons to donate back from our negatively charged carboxylate, which can then decarboxylate or remove that one, and then deliver our hydride to our NAD, thus forming, scratch that one, thus forming NADH. Okay, this gives us an enol form. And I apologize, not the best drawing in this. And again, our enol can tautomerize. Can tautomerize to our ketone form. let's take a look at some other biological oxidizing agents. One example is the heme-dependent monooxygenases. Cytochrome P450s are important enzymes in the hydroxylation of endogenous substances, as well as a wide range of xenobiotics. These are things like drugs and other chemicals that you're exposed to. All cytochrome P450s accomplish their functions using the same basic mechanism, but each enzyme has been adapted to dismantle particular groups of chemical structures. They all use the same active core, which is shown here. Let's look at how the enzyme gets to this point and what is a reaction that this active core can actually perform. Let's start with water bound to our heme group. The iron in this complex is octahedral, low spin, N+3 or D5. If we populate the orbital diagram, it looks something like this. As the substrate enters the active site, okay, in other words, this RH, as it comes in, it displaces the water, and the iron adopts a 5-coordinate high spin state in which the iron is out of the plane of the porphyrin ring, giving a kind of square pyramidal shape, changing from low spin to high spin. So let's see what that looks like. Makes it easier to reduce the heme group. In other words, it will accept electrons more readily. The one electron that is added here in this last step here is probably coming from FADH2, since it can do the one electron reductions, giving us now iron in a +2 state. Remember, molecular oxygen behaves like a diradical and can react with one or can react with our heme group. So we can have O2 binding to that iron, thus getting back to our octahedral complex. Again, we can donate one electron in this reduction, and our heme will form this peroxy anion. This negative charge is then readily protonated. Note this is a 2-electron arrow if we draw it out. Not a 1-electron arrow, 2-electron arrow. The next step that we have to do is actually generate that high energy oxoferryl heme complex. And one way that we can do this is actually protonate. Again, this is a 2-electron arrow. Go grab that hydrogen, and if we look at this, we're going to actually produce water. So we protonated it, lost water. This is our high energy intermediate. In fact, we can draw resonance structures to show how that's stabilized. Notice I've moved 1 electron from our iron, going from iron 3 to iron 4 up to here. We can also draw an intermediate, much like was on a couple slides ago. So we can actually stabilize this to a certain degree through resonance. 1 electron transfer resonance, that is. This intermediate finally reacts with our substrate by abstracting a hydrogen radical. We then get our R group over here released, and this can recombine with another radical. And let's drop that back over there. To give our final hydroxylated product, and it gives us our iron compound back ready to accept another molecular oxygen and undergo another reactive turnover.